This video is an introduction to Chapter 7 in PreCalc, which is called Analytic Trigonometry. The big idea behind all of the concepts that we cover in this chapter is going to be, how do you solve an equation for an unknown angle? In other words, how do you solve the equation on the right for theta? The first section we're going to cover in this chapter is section 7.3. We're going to be jumping around a little bit, which is called manipulating trig identities. A trig identity is an equation that says two expressions are equal and can be substituted for one another. For example, we know that cosecant is the reciprocal of sine, so 1 over sine. Therefore, if I ever saw 1 over sine written on a paper, I could easily get rid of that and put cosecant in instead. And you might want to do that so that, for example, you didn't have a fraction. There are actually a lot of trig identities that you already know. For example, you know all the reciprocal identities already. You know that cosecant is 1 over sine, secant is 1 over cosine, cotangent is 1 over tangent, and we haven't seen them written this way, but you could also go backwards. If you had 1 over cosecant, that would be the same as sine, because flipping cosecant gets you sine. 1 over secant would give you cosine, 1 over cotangent would give you tangent. We're going to find that it's often desirable to replace fractions with not fractions. So if you ever see a trig function on the bottom of a fraction, these reciprocal identities give you something you can do to change it into something that's on the top. So if you ever see secant on the bottom, change that to cosine on the top. It turns out you also know the identities that are officially called the quotient identities. Tangent is sine over cosine, cotangent is cosine over sine. These could be useful again to get rid of a fraction, but more often they are used to turn tangent into sine over cosine, because sometimes it turns out it's easier to work with sines and cosines than it is tangents and cotangents. You should already be familiar with all of the identities that I just mentioned. Now we're going to present a new set. These three identities are called the Pythagorean identities. As time goes on, you're going to want to have the reciprocal, quotient, and all three of these Pythagorean identities memorized. To help with that, I'm going to show you where this first one comes from. It's not just a rabbit that we pulled out of a hat. And I'll also show you how, if you memorize the first version, the other two versions can actually be built off of the first one pretty easily, which makes memorizing easier. Before we do that, I want to say one quick thing about exponents and trig functions. The way that you would say the first version of the Pythagorean identity is sine squared theta plus cosine squared theta equals 1. That notation with the squared between the sine and the theta is the same as writing sine theta all squared. However, no one ever writes it the second way with the squareds on the outside. You'll always see it between the trig function and the theta. So that is the way that you should write it and read it. Sine squared theta plus cosine squared theta equals 1. Now, where does this Pythagorean identity come from? To figure this out, we're going to imagine a circle with a radius of 1, or a unit circle, and a point called xy drawn anywhere on the circle. I drew it in the first quadrant, but it doesn't have to be. I zoomed in on that point a little bit, and I drew a dotted line that connects the origin to that point. Then I dropped a line straight down from the point to the x-axis to make a little triangle. I called the angle between the x-axis and the slanted line theta, and then I knew that the horizontal side would be the same length as x, the vertical side would be the same length as y, and since this is a unit circle, the hypotenuse is 1. In this green triangle, we can see that the sine of theta is opposite over hypotenuse, or y over 1, or y. Cosine is adjacent over hypotenuse, or x over 1, or x. And by the Pythagorean theorem on the three sides in this right triangle, x squared plus y squared equals 1. If we put sine and cosine into the Pythagorean theorem, where the x and the y are, we get cosine all squared plus sine all squared equals 1. Changing to the notation of having the squared in the middle, and just putting the sine term first, because that's usually the way it goes, gives us that identity, sine squared plus cosine squared equals 1. And you can see why this is called a Pythagorean identity, because it comes from the Pythagorean theorem. If you memorize that first version of the identity, you can get the other two versions that I showed you at the beginning very easily. The second version comes from taking the first version and dividing all the terms by cosine squared of theta. You can make the third version almost the same way, except that you divide all the terms by sine squared instead, and this gets 1 plus cotangent squared equals cosecant squared. So the takeaway idea here is that if you know the first version of the identity, you can always create the second two for yourself by dividing either by cosine squared or by sine squared. Now, the last thing we have to talk about is that sometimes the Pythagorean identities don't show up in their original forms, they show up in manipulated forms. What I mean by that is that you could rearrange the terms in the original identity to create another equivalent identity. I've got two examples on the screen. In the top one, I subtracted cosine squared on both sides, so the identity became sine squared theta equals 1 minus cosine squared theta. In the bottom one, I subtracted 1 on both sides and cosine squared on both sides, so that the identity became sine squared minus 1 equals negative cosine squared. So basically, anytime you see a sine squared, a cosine squared, and a 1 hanging out in an equation together, you want to be suspicious that it might be a rearrangement of the Pythagorean identity. Of course, you can rearrange the other versions as well. Here I showed two rearrangements of the second version, one by subtracting tangent on both sides, and the other one by subtracting 1 on both sides. You could also do it with the third version. In the top one, I subtracted cotangent on both sides and cosecant on both sides, so that I get 1 minus cosecant squared on the left and negative cotangent squared on the right. In the bottom one, I just subtracted cotangent on both sides, so that I ended up with 1 equals cosecant squared minus cotangent squared. All of these options are valid manipulations of the Pythagorean identities, so they're considered identities themselves. You do want to be careful, though, and be on the lookout for equations that look similar to these valid manipulations but actually aren't. I'm calling these fake IDs. For example, sine squared minus cosine squared equals 1 is not a Pythagorean identity because there's no way to change that plus in the original identity to minus through valid algebra. Similarly, we know that tangent squared equals 1 minus secant squared has to be a fake identity because above we showed tangent squared equals secant squared minus 1, and it can't be equal to two different things. Finally, 1 plus cotangent theta equals cosecant theta is a fake identity. I can tell this because it's missing the squared terms, and all the Pythagorean identities have to have squared terms. These properties don't hold if the squares are missing.